Hello all, welcome to my channel. I'm back with another video. This is the part 5 of the ongoing series on 5S of Spark challenges that we are doing. In this video, we will go through and see how storage layouts uh, affect the job's performance in Spark. So let's get started. So in Spark, the performance of a job uh, is greatly hampered or improved based on the layout of the data that we have. When I say layout, it's not only on the physical layout, it's both the physical as well as the logical layout. I mean, the physical layout becomes the files that are written onto object storage or HDFS, and the logical layout or the memory layout is how data is partitioned in memory while Spark is doing the processing. So those things actually affect the job's performance a lot. And if if we do not have the right set of configurations and right set of layouts defined for the job, we will see issues which are storage linked issues that will come in Spark. What are the common ones? For example, the common issues related to the Spark's storage component is suboptimal file formats. Let's say if we have file formats which are not designed for the workload that we are trying to achieve, is something will cause issues. For example, let's say if we are working with streaming data and we have, let's say, a CSV file format that is being written on disk. Uh, that will cause an issue because streaming data is something which requires a lot of frequent updates, which CSV will not be the right choice. Maybe Avro is the right choice, or the newer versions of table format which is there. For example, let's say Hoodie, it, which is designed for real-time updates. It has upsert capability, so that becomes one option. So choosing the right file format or table format uh, decides what will happen with what will happen to the performance. For example, if you see, I just this is an experiment that was done, and we see that for 100 million records file size, we when we write it to JSON, its size is 1 GB, and write time is 3 seconds. And while we read the back the data, it reads in 6 seconds. See the Parquet, the same data written in Parquet file format is only consuming 85 MB, which is way less than what JSON was offering or what CSV was offering. And also because the file sizes are small, the write time is less. The read time is even see it's almost to the factor of 10. So zero point 0.6 second versus 6 second. It's just very smaller fraction of time that it takes. So we have to decide. I mean, it's basically we need to decide the right format type for the job we are doing. For example, if we are doing a lot of analytical work, uh, Parquet or Avro, not Avro, Parquet or ORC can be a right approach, a right file format, because those supports both uh, predicate push down, aggregate push down. So those optimization will come into picture when we are running the job. Some formats do not fully support aggregate and predicate push down. For example, JSON has support for predicate push down, but it doesn't have any support for aggregate push down. So depending upon the workload that we are doing, we should be deciding on the file size that file format that we should be using, and also see the layout of different file formats that we have. So layout of the first above one is the row and columns. So it is a logical table, and how it is written on the disk. The row-oriented files will have each rows written back to back. The challenge with that approach is that if we, let's say, column one is of type one, and let's say string type, column two is, let's say, an integer type. Because this is sequence, this is written contiguously on the disk. If we want to do some compression, some encoding, that will require us superset of both the data types. But while we are looking at column oriented ones, here that challenge is not there because the type of the contiguous blocks are same. So one for the so let's say if we have rows split on, let's say, 100 rows we had, so 100 contiguous of same data type, the compression or other algorithms or other encoding things that we want to do will work faster. So hence the memory format, sorry, the file format is very important while working with Spark. Then other thing is the other important thing is how we decide the file size that should be there. So for example, this is needed because file size decides the number of jobs that will come, or not jobs, number of tasks that can run in parallel. So parallelism of that gets decided not directly on the file size but linked to file size. For example, if we have let's see here, if our workers or executors have capacity to handle, let's say, 256 MB of data, and if we have, let's say, a file, Parquet file of 484 MB. So if we do, and our max partition byte is set to 128, in that case it will create four partitions and then it will do the processing in that way. But if we set the max partition file size to 256, it will create only two partitions. So these two different approaches will cause different parallelism, and how we decide that what should be the partition block size is based upon this number partition bytes. I think this is wrong. It should be 256. By mistake, it is 128. So yeah, means the gist is that if we create it, so we have to take a balance between how many partitions we want to be created for this particular files which are there in the file system. Because if we create too many partitions, then there will be overhead of running too many executors. But if we have too big a partition size, then only is here. It's, if you see, four processes running parallelly to compute whatever we need to compute versus two processes running. So the time will get means longer and longer if we have larger partition size. But there is another thing that if we are processing data which are larger and can fit in memory, so once it is loaded, it will be easy for them to the executors to work on those things. So it's a balance that we'll have to decide that what should be the right partition size. Then other big challenge that is there with Spark is small file problems. Spark is more suited. Spark works well with uh, cases where we have larger files rather than smaller files. The reason for that is Spark, whenever it opens a file, it has an added cost on that. That, for example, there is a concept of open bytes cost, open byte cost or open cost bytes, something like that, which says that for opening each file or creating a new partition will add an overhead of, let's say, 4 MB. So that thing is actually an issue. So if we have larger files, we will be needing lesser IO, because, for example, let's say if we have too many files, first cost will come off the file listing itself. Then each file has to be opened, a network IO buffer has to be created, then the data has to be read, and then it has to be closed. And while reading that data, Spark also has to store the metadata of that particular file, that because that needs to be available and that needs to be present while we create the data frame. So, and that data resides on the driver itself. So let's say if we are reading 1 lakh files, so we will have metadata of 1 lakh smaller files. But let's say the same data can be condensed into, let's say, 1,000 files, then only the metadata of 1,000 files will be needed, right? So that way, its small files also cause a lot of challenge in Spark. And this is one test again, where we have 100 million records in 8 large files versus 100 million records in 1 lakh small files. So if you see, with 8 large files, Parquet was able to process that in 0.6 seconds, but with 1 lakh small files, it was taking 5.8 minutes. So you see, this is a very huge gap that comes if we have the data amount of data getting processed is same, but because we have too many smaller files, the overhead is higher and hence the job gets slower and slower. See, and the same thing with Avro, 0 0.9 versus 5.9 minute when it comes to processing large number of smaller files. And I was mentioning that each file incurs these costs. Then we have another case where we have schema issues. Schema issue, it's not an issue. I'm saying yes. Challenges with schema is that if we have data which does not have an schema defined, then it's Spark has to identify the schema and do the schema enforcement or typecasting, up downcasting, upcasting, those kind of things. And we again the test was run for the same 100 million records with and without schema. So if you see with schema, Parquet was able to load. Sorry, without schema, Parquet took 5.8 minutes to load the data for 1 lakh files, and for read time was 0.6 second. But when it comes to with schema, it only took 33 seconds, while it took 0.4 seconds in larger files. So with schema and without schema also does include a lot of lot of overhead to Spark. Then we have another thing is called inefficient data scanning. So if the data layout, both physical and logical, does not match the query pattern, the job's performance will degrade. When I say query pattern, it means what we are doing in the pipeline or in the Spark job. For example, let's say if we are trying to do group by based on certain keys, and that, but the layout in the files when it is read, or the layout in which it is stored in the file system is different than that, then we will not be able to, let's say, prune the partitions. We will not be able to push the aggregates. We will not be able to leverage the predicate push down. So stuff like that will happen. So we should be having a file format that has the right layout as well to suit our jobs requirement. A compression algorithms is also there, which dictates that of how, because if the data is compressed, there will be lesser I/O while we are reading the data. So that is another part. And there are certain configurations that is there related to storage, like memory fraction, storage fraction, memory overhead, off heap, and off heap size. So these do help in Spark's processing of data. So memory fraction is the amount of memory that will be available for unified memory that is there. And then storage fraction is how much of that unified memory will be allocated for caches, and executor memory is for buffer memory or any overhead memory that we have that goes into execution memory. Extra, we can add extra overhead memory for serialization and deserialization. Off heap is something that we can use uh, for things like unsafe row, which is there in tungsten, or sorry, native engines which do not work with JVM, and that will help us speeding up the process. Uh, so we saw some challenges that what are there and how we can solve those challenges for data storage. One is use the specialized format, like as mentioned, Parquet or ORC. Optimize data partitioning. So data partitioning is so there is, I have a different blog as well, and video as well is there, which talks about how we partition data and how what affects size of what affects the number of partitions. That, let's say we are reading a Parquet data, so what affects its number of cores in the cluster, estimated file size, number of Parquet files, number of row groups in Parquet file, and then the max partition size. So those things decide how many partitions gets created. And while reading from databases, we have option of choosing the partitioning column, lower bound, upper bound, and then we decide what should be the right partition. So similarly, here we need to avoid too many small partitions and too few large partitions, because this will cause skew, this will cause too many overheads. So we have to balance that. And generally, the good practice is to have partition numbers equal to 2 to 3 times of your available executor cores. That also should be the maximum, like maximum in a sense, the maximum amount of parallelism you need in your job you have to decide based on that. It's not that, okay, let's say in one stage you have, let's say, only 10 tasks are happening, so you decide, okay, I will have 10 partitioning of 10. So that doesn't work. So you have to take in account of the whole job's max parallelism and then decide what should be your partition size. Choosing the right compression like Snappy or LG4 will help. Tuning the partition size, like once we have read the files, if we are, let's say, when we read from disk and the partition was not suiting to our query requirements, or let's say in between we are changing the pattern. So in those cases, we can tune the partition size by either increasing the number of partitions or decreasing the number of partitions. AQE also helps in here because this can dynamically increase or decrease the number of partitions, do the coalescing and stuff, and help us in the job. And the physical and the logical layout is something that we can. So while let's say if our job is writing something and that is being consumed by another Spark job, so if we can do the right physical layout based upon the downstream applications consumption. For example, if the downstream application filters based on year column, then we while writing itself, we can do a partition by year so that when it is written, the next time when it will be read, the predicate filter can be applied in that way. Then, if we are using iceberg or delta table formats, we can run Z order, or we can even do liquid clustering and stuff like that. But that is a different topic we will discuss. This was more on the Sparks side. So this is all about the storage challenges and how we can fix it. Uh, so this completes the series, and then we'll create new videos on Spark concepts that will be helpful for, or that I believe will be helpful for all to know. Uh, Thank you. Have a nice day.